We're going to be talking about generating magnetograms. And so this is joint work with my student, Richard Higgins. Both of us are actually computer vision people by training. So this is work that's been done with a lot of great collaborators on solar physics and space weather. And so let's just get started. And so the sun is, of course, a source of large amounts of interesting phenomena. And in particular, the sun's magnetic field produces things like solar flares and coronal mass ejections. And so therefore, there are a lot of instruments that monitor the sun's magnetic field. And in particular, they produce things like, for example, magnetograms. So this is a magnetogram from the Solar Dynamics Observatory's Hmi instrument, showing the flux density. And these are magnetograms of the photosphere of the sun. And these magnetograms actually sort of serve as a foundation for much of the space weather science pipeline. So you get a magnetogram, and then people, for example, large numbers of people here at Michigan who do space weather modeling use these as boundary conditions for their models. And then people who do flare prediction, for example, use features that are derived from the magnetograms as features for their flare prediction systems. And so, for example, you pull out a bunch of features from an active region from this magnetogram. And so today I'm going to be talking about how we can improve and sort of produce better or different magnetograms using deep learning. And so just to give you a sense of how these are actually normally generated, the basic idea is this. You can take the magnetic field parameters, so like the density, the flux density, the field inclination, the field's azimuth, the velocity of the plasma that's generating it, a bunch of thermodynamic parameters. And what you can do is you can have a forward model that explains what types of observations you'd expect to see. And these observations are going to be observations of polarized light. And so, for example, Hmi on NASA's SDO mission observes 6 band passes of polarized light. So that's sort of 24 observations. And you can basically, given a magnetic field, generate what light you should see. And the idea is that you do what's called a Stoke Conversion, where you try to figure out what magnetic field best explains the observations that you do have. And so you can minimize the distance to the observations using an optimization technique. So typically it's some sort of standard nonlinear least squares type approach. And different instruments, of course, observe different light. And so they will have a sort of different inversion in the sense that there's a generic inversion technique, but then, for example, SOT-SP or SP, which is on the Hinode mission, absorbs many more band passes. And so it sort of, it has a sort of, it will produce a different sort of type of inversion because it can observe, it has many more observations to pin down the actual field strength and all the other parameters. And so the big research question that I've been interested in for the past few years has been, can we emulate and improve these pipelines with deep learning? And although I'm showing you like a single slide to sort of illustrate the idea behind these pipelines, I say, okay, you just do it by optimization. These are generally quite complicated pipelines, and there's tons of calibration, and there's tons and tons of technical details. Okay, so let me just introduce how we sort of produce the sort of can emulate a pipeline. And the idea here is that if we have inputs and outputs from a single pipeline, we can try to produce some sort of parametric function that will produce, sort of emulate, or be able to produce synthetic versions of the pipeline's outputs. So, for example, we might have observations from the Hmi instrument and we have its pipeline output. And what we'll do is we'll try to learn a function f, which has parameters theta, and we'll try to basically learn a function, the parameters for this function, so that they minimize the loss on a training set. So given a bunch of inputs and outputs, we can find the best fitting function to this model. And that's sort of like the deep learning approach in sort of one slide. And the idea here is that once we found the parameters theta, we can then apply this function to totally new observations. So if a new set of observations come in, rather than doing the inversion technique by minimization, so using an optimization technique, you just do a single feed forward function. And since this is a machine learning audience, or there are people here who are very interested in machine learning, I'll just briefly explain some of the stuff that we do. We actually formulate it as a regression by classification approach, which enables us to sort of produce a distribution over discrete values, which enables us to produce sort of single outputs, as well as also produce sort of estimates of uncertainty. So we can sort of, by producing this distribution, we can figure out which pixels of the inversion are we confident about and which ones are we not confident about, which is quite nice. And given the limited time, I can't explain all the details, but there's a sort of paper which explains it. So we applied this to going from Hmi inputs to Hmi outputs. And what we've been able to do is you have a system which is ultra fast. So this takes about 6 seconds on a GPU versus 30 minutes for the previous sort of optimization-based pipeline. And of course, it's hard to make comparisons between GPU implementations and CPU stuff, but this is, it's a 6 seconds for a very unoptimized implementation. So just framing it as a neural network can accelerate things tremendously. It's quite accurate, so we're able to get the active regions quite accurately. So these are active regions that typically have 1,000 Gauss magnetic field strength, and so we're getting errors around 17. The inclination and the azimuths are typically single-digit numbers. And what's fun is that it actually gets a lot of issues that the system, that the current pipeline has right. So HMI is known to have oscillations in its data. So if you look at the average field strength, there's a 24-hour oscillation, which produces this entertaining sort of cat ears-like artifact. And our system is able to actually emulate these quite accurately, which is quite exciting. Because what this means that if we can emulate them accurately, this might mean that if it now takes only 6 seconds to invert a single instance, this might mean it might be a lot easier to fix these oscillations. So being able to reproduce the bugs here is actually quite good, since it might let us fix them more easily. So that's how you can produce an emulation of a single pipeline sort of magnetic field generating approach. And this is, of course, not necessarily a new idea. There's work going back to 2001 on trying to do learning for Stokes vector inversion. And so we're not obviously not the first people to do this. This paper just kind of tries to do it with CNNs and in as modern a way as possible. One of the things that we realized you could also do is this also enables you to tackle sort of new problems. And so let me show you what I mean by this. And so here's the sun again, and it gets observed by multiple instruments. And these instruments tend to have complementary design decisions. So HMI on SDO has a really fast cadence. It produces like a global snapshot of the full disk of the sun. And on the other hand, it produces stuff at a moderate spatial resolution, and it only observes 6 wavelengths. And so its results are not as accurate as other instruments. And in particular, there are things like SP, which observe things at a really high spatial resolution, observe tons and tons of data, and actually produce more parameters. So it can actually separate out properties such as magnetic, the fill factor of the magnetic field. But at the con of having a slower cadence and being a scanning slit instrument, which means that it slowly scans a slit across the sun, so you actually don't get a single global snapshot. You get essentially pictures taken at different points in space and different points in time. And it also has a very small field of view compared to HMI. And so these instruments have complementary pipelines. And so of course we can build inversion techniques for each of these pipelines, and people have done this. One of the things we realized we could do is we could actually build inversion techniques which go from one instrument's observations to another instrument's inversions or magnetic field. And so we produce a system which we call SynthIA. And it takes HMI observations and produces, or attempts to produce, inversions or outputs that are very similar to the SP instrument. And so it inherits the pros of the HMI input, which is a really fast cadence, getting a global snapshot and being full disk. And it should also inherit many of the properties of the SP instrument, which is that the accuracy is generally considered to be higher. It also produces more parameters and generally considered to be a higher quality inversion. And the con, of course, in all of this is that this is all learning based. So validation of this is quite a bit more challenging because we can't actually get ground truth full disk data for the SP instrument because there isn't an instrument that can observe the full disk with 112 wavelengths at the resolution that HMI has. So it's basically validation is quite tricky. So the idea here is that we're going to take as inputs, we're going to take observations from HMI, which are sort of co-aligned with SP data. And we're going to train the same exact inversion system. And the big picture idea here is that all we need is training examples. We don't necessarily need to have an actual working pipeline that goes from HMI observations to the SP output because there isn't one. But if we can co-align these instruments, then actually we can produce this sort of synthetic inversion. And this at first feels a little bit like magic because, well, if you can extract this information from the HMI data, why can't you extract it in the first place? And the key idea is that each individual HMI pixel, which is used in the inversion, and these inversions are typically done pixel by pixel, it tends to have less information, but if you look at a full neighborhood of pixels over a large region, this has tons and tons of information. And so the machine learning can extract this information out, even though we don't necessarily have a good physical model for it. And so the way that we get these aligned data is we take data that both instruments observe. And so there's HMI, this is the continuum image. There's Hinode, which here's a continuum image from it as well. And we can use standard computer vision techniques to line things up and then do stuff like optical flow to correct for the solar evolution that takes place as the SP data gets captured. And this technique works quite well. Its sort of failure modes are stuff like quiet sun, which is not necessarily very interesting. And it doesn't work well in poles, but we have a forthcoming technique which fixes a lot of this sort of stuff and is substantially better. But for now, this works quite well, and we get lots and lots of active regions sort of all over the disk. And so let me show you some outputs. And so this is sort of a cutout. So we have in the top row, we have an actual output from Hinode SOT-SP. And I'm showing you sort of 4 representative things that are produced in an inversion pipeline. There's the flux, there is the fill factor, which is what fraction of the pixel is occupied by a strong magnetic field. There is the field's inclination and its azimuth. And you can see that in the sort of the weak regions where there's not very much basically magnetic field, the azimuth tends to be noisy. And HMI produces quite similar results. You can sort of spot some of the subtle differences. One of which is that HMI doesn't actually produce a fill factor. It's set to 1 because there isn't believed that there's really enough information in the HMI observations to nail down the fill factor versus the magnetic field strength. And then here is our output, which is from our system SynthIA, and we sort of call its output Synode because it's synthetic Hinode. And you can see that we can also produce an estimate of the fill factor, and our, everything sort of lines up quite nicely. Now, there's some subtle differences in the inclination that you can possibly see, but what I'm going to do is I'm going to actually sort of zoom in because these are cutouts. These are a small part of the disk, but even now they're still a little bit hard to see. So let me zoom in on a 75 arcsecond cutout. And so here is on the left is the actual result from the SP instrument. And on the right is our result. And you can see that the results are pretty similar. You can see that there's a bit of blurring in our results, but generally the general structure is quite accurate. And I'll just show you a difference image. And so this is the flux density. So this is from 0 to 5,000 Gauss. And so this is a difference image where white is, they are the same, and then blue and red are either underestimates or overestimates. And so you can see that there's generally relatively good agreement. Some of the fine detailed structure is wrong. And this is because, of course, our outputs are a little bit blurred. And this is likely due to the alignment not being precise enough. For comparison, I can show you the HMI data. So here's the HMI data. And it looks a little bit different, but let me just show you the difference map. The difference map shows that there's really systematic differences. And this is a well-known phenomenon. The instruments produce quite different outputs. And so you can see here that some parts of the output are substantially underestimated. Some parts of the output are substantially overestimated. And generally, the two really don't agree very much. And this is pretty pronounced as well in stuff like inclination, whereas here is our results for producing inclination. And you can see that there's generally good agreement. Again, it's a little bit blurred, and this is just a natural effect of the alignment. So we can't precisely get the ground truth perfectly aligned, as well as also deep networks tend to also produce kind of slightly blurry images if they're not precisely sure. And then for comparison, let me just show you the HMI, and you can see that there's a substantial difference in terms of qualitative stuff. So if you look over here, the inclination angles are there's these sort of thicker networks of sort of dark blue. And if you compare that with HMI, these networks are substantially thinner. So before and after. And so despite the fact that our system is using HMI inputs, it's able to produce outputs that very closely resemble the Hinode data. And there's a lot of quantitative results that I'm not going to get into due to the interest of time, but there's a lot of validation. And one of the things that I learned is that in this process that we had a lot of domain experts. And so one of the great things about this work was it was a very collaborative environment in which we essentially, the validation was driven by domain experts who are very skeptical of these results, which is great. And so we looked at all sorts of stuff. And so there's stuff like, for example, bivariate histograms, where you can look at sort of confidence intervals of basically what's the relationship between, on the y-axis our predictions, on the x-axis the actual Hinode data. And most of our predictions are very close to the y-axis line. So this is a log plot actually. And there's mainly sort of symmetric noise. It's a little bit of, there's like scatter as opposed to some sort of bias. And if you look at, for example, comparing instead the HMI data, there's a systematic distortion, and HMI data is much closer to 90 degrees on average compared to, for the inclination, compared to SP data. And what was nice is that this is also a well-known effect that other people have seen as well. But our system, despite using HMI data as input, produces data that's much, much similar to SP. There's also other fun stuff. So the HMI pipeline has oscillations in all sorts of outputs. And so you can actually use different inputs for SynthIA. You can it's a system, you can go from AIA data to, for example, SP, magnetic field strength. You can also add in things like HMI continuum. You can use full Stokes data. You can try different combinations and mix and match inputs and try to produce the same output. And these, due to how the data comes, produce varying amounts of oscillations in its outputs, because essentially the oscillations appear in the inputs as well. But they also produce varying amounts of accuracy. And so I'm showing you 4 of these things using AIA data. So this is just intensity data. It's actually not even from the photosphere, but we can get reasonable estimates of the magnetic field strength. If you add in a little bit of information, which is just the intensity image in the photosphere, you get actually quite accurate data and you get much reduced oscillations. And then if you actually use the full Stokes data, you actually get even better accuracy compared to the Hinode data. And the oscillations are quite a bit smaller compared to using the HMI pipeline, which again has these cat ear results. The cool thing is that once you train on these cutouts, you can actually run this on the full disk. And so these are outputs of the parameters like the field strength, the inclination, the azimuth, and also the field in heliographic coordinates. And you can run this on the full disk. And in fact, here's a video of it running. And this is basically about 2 months worth of data. And it's really fast. And so my student Richard cooked this up in sort of an afternoon, whereas this is something that would take sort of, like something like on the order of approximately a month. Don't quote me on that, for the pipeline to produce, just because our system is, we're running on the GPU, and it's able to produce these full disk outputs really, really quite fast. So you can see that it produces actually quite nice stuff, and it's always fun to watch your outputs move. And so here you can see that the sort of sunspots going across the sun. You can see the outputs from our system. So with that, I want to sort of conclude with sort of conclusions and big pictures. So one of the things the thing I told you about today was there's SynthIA, which produces outputs like one instrument while using the inputs of another instrument. And this is a relatively straightforward idea, but I think it's able to unlock a lot of neat things because you don't actually need a physical model to go between these two things. You have well-defined physical models for each of these instruments, and there's a challenge, which is the validation is going to be quite a bit harder. But I think this is exciting because it enables you to capture best of both worlds type data. So the goal here isn't to replace instruments, it's to sort of get more value out of these instruments. And our long-term goal is really to interconvert everything. And there's wonderful loads of instruments that produce these magnetograms, and we'd love to basically be able to produce the best magnetograms possible for the community. And so it's been wonderful to be with you, and I'm happy to take any questions.